we'll get to Glenn Peters, who will try to set a new record by showing 100 slides in 17 minutes, I guess.
I have 17 minutes.
You want to get a question afterwards, right?
Okay, thank you. So I'm going to talk about allocating negative emissions to countries. Do we have a pointer, by the way? Okay, thanks. And I guess there's a continuous theme here with some of my work, or our work, I should say, starting to look at the country level, going from global to country, where it sort of comes back to home, if you like. So this is work involving my colleague, Robbie Andrew, who some of you will know. Oliver is also included, and Detlef van Vuren, and you'll see some of the results from the image model as well as I go through. So first of all, a bit of background. One nice feature of the carbon budget approach, I should say both Oliver and I had sort of critical comments on the carbon budget approach last week, but I'm going to use it here. One nice feature of the carbon budget approach is it's a very easy and transparent way to share out or allocate emissions to countries. It's easy to overinterpret the results of doing that, and I tend to think of this sort of sharing or allocation as very useful for comparing countries, not for prescribing what countries should do, although many people fail to make that distinction. Negative emissions actually make the sharing or allocation to countries much more difficult. So if you start to get into the maths and put some negative numbers in there, then all your equations tend to go crazy. So it makes things much more difficult. But if you can do it, it leads to simple and transparent approaches. So we had some critical comments from Tim this morning on integrated assessment models. Here is the sort of other end of the spectrum, which is something that's quite simple and transparent, perhaps easy for people to grasp. And that can be useful for understanding mechanisms, what's going on, and so on and so forth. Everything has its advantages and disadvantages. Just an example of a simple approach that's quite applying this as a simple approach and easy to communicate. This sort of figure here, which is done by my colleague Robbie Andrew, it's also been shown on the Carbon Brief website, and it does extremely well on social media. So this is links to some of David's work. People really love this figure. It's simple. If you do it as an animation, it shows, if we started climate policy back in 2000, how much easier it would be compared to if we delay. Now you can go into fancy integrated assessment model calculations and look at costs increases and all this technical stuff, but this really grasps people's attention. This is something we did a few years ago, comparing the country's emission pledges to a carbon budget, for example, for 2 degrees. There's a sort of line down the middle there, which is 2015, and the projections go out to about 2030, and you pretty much see the top 4 emitters, US, EU, India, China, pretty much eat up all the 2-degree budget. But this has nice features. One disadvantage of this approach is it doesn't have negative emissions. So maybe they're not eating up the carbon budget if you allow negative emissions. So the approach we initially had does allow some negative emissions as long as emissions don't go in total net below 0. And so the general approach or idea in this paper is to allow emissions to go completely negative, go below 0, and still do that sharing. And there's many ways that you could do that. We've chosen a way here which I'm going to present. May not be the optimal way, but it's a way. So allocating negative emissions. This is a figure from a paper from Johan Rockström, published last year on rapid decarbonisation. It's a 1.5 degree scenario, or consistent with 1.5 degrees, coming from the MESSAGE integrated assessment model. So that's out of IASA. And the grey part at the top of the figure is the positive emissions from fossil fuels industry, and the dark grey is land use change, or the positive land use change. And below the 0 line you have the land use sink, which is a net basis here. So the orange and the yellow is what they called engineered sinks. I think a very nice term. In the model, it's bioenergy with CCS. So they've split out the gross positive and gross negative emissions. And from this, you can get a positive carbon budget and a negative carbon budget. So this figure here just shows the cumulative emissions from 2017 up to the end of the century, which is essentially one definition of a carbon budget. And you'll see there the net budget. When you add the grey and the colours The net line, which is the black line there, goes up and comes back down. It changes over time, so the carbon budget is going to be very dependent on how you define it. This is one of the issues brought up in our commentaries on carbon budgets last week in Nature Geoscience. But if you split the budget into the gross part and the negative part, so you consider the greys together and the sort of yellow-orange together, then you have two, in a sense, positive components that you can start to share out. So the idea here is to take the positive parts, share those to countries, take the negative parts, share those to countries, and then add the results back together again. Once we have those budgets, so we take these budgets at the sort of right-hand side of the figure there, the positive emissions, 850 billion tonnes, and so on. We take those budgets and then use stylized functions to share those emissions or distribute those emissions over time. And here I show the results from the message model with the dark lines and the dotted lines, or the solid lines, and the dotted lines are what, sorry, the dotted lines are what come out of the message model, the solid lines are what comes out of our stylized functions. We haven't tried to fit the curves here. This isn't a curve fitting exercise. This is just take, here's the budget, here's a stylized function, plot it, and compare it to the modelling results, and it's basically the same. Like you almost fall off your chair when you see this sort of agreement. The sort of functions that we chose there, which comes from earlier work, we hadn't tried to do this comparison before. These are functions that we had previously come up with. The functions, the positive emissions have an inertia component, so it initially follows the current emission trajectory before it merges into a function with exponential decline. And we also assume that you can't go to zero. There's some residual emissions at the end of the century. The negative emissions we took as a standard sort of S function, which is common in deployment of different technologies, and we just took a cosine function. And I mean, the agreement here is pretty amazing. This is from one model. You can do the same with the image model, which is coming from Detlef van Vuren's group. The agreement is not quite so good. It's very good on the positive side, but on the negative side, you'll see the image model has much faster deployment of negative emissions, and it reaches its sort of, if you like, its plateau much earlier. So there's some differences there, but I still think this is pretty good. Of course, there's other integrated assessment models we could compare against, but that's something that will come later in time. And this is just sort of showing one of the advantages of this sort of approach. Once you have these stylized functions, you can just, in the matter of how long it takes you to key it into the keyboard, you can do different plots, different functions, making different assumptions. So what happens if we have all the negative emissions available, which is the green line? What happens if we just say there's half the negative emissions, and what happens if there's no negative emissions? Those three lines there, and you can quickly get a comparison of how mitigation rates change, et cetera, et cetera. This sort of thing is quite easy to communicate to people, and you don't need to wait on modelling results from complex models and so on. So once we have these gross positive and gross negative emissions, the next task is to distribute it out to countries. So what we do is we allocate a budget to each country, and then once we have that budget, we allocate the pathway, distribute that budget over time. So the allocation here, I'll show you what sort of allocation, if you like, in quotes, rules we used. And I just really want to emphasize, I'm going to say this many times, we're not trying to discuss what methods of allocation you should use or what ethical issues come up, but we just want to test the method. Later on, we'll come back and look at different strategies to share that will allocate those emissions. We use two methods. This is coming from earlier work as a bit of a background to why we chose these two, but one option is we share emissions based on the current population, which is a bit like a per capita, and the other is we share it based on current emissions, which is like grandfathering. Now, of course, many will not say this one down the bottom is fair. Some will say the top one's not fair either. You can get into historical emissions and all sorts of different things. Again, we're not going to get into those here. We just want to demonstrate the method. One issue you have with the positives and negatives is if you want to share them in the same way. And when you go through this analysis, you quickly learn that you can't share them in the same way. I've made a spelling mistake, probably the most critical word on the entire presentation. We allocate positive and negative emissions asymmetrically, and not symmetrically. So if we share positive emissions by population, we share the negative emissions, the negative components by emissions. If we share the positive emissions by emissions, we share the negative ones by population. And it's easy to show, or easier to explain why we do that if you just look at a couple of examples. So if you take a country with low per capita emissions, India, for example, it will get if you share based on population, you'll give it a much bigger positive emission allocation, but you don't want to give India, therefore, a very big negative emission allocation. In a sense, you're trying to give them less responsibility or less emissions to reduce. So if we share the positive emissions by population, they'll get a smaller quota for negative emissions, and you can go through the same arguments with high per capita emissions where you just flip it around the other way. And again, this is overly stylized. There's many ways you can do this a little bit differently or improve it, but this is just to demonstrate proof of concept in a sense to see if it's worth following this approach. So I'm going to get into some results. There's a lot going on in this figure, so I'll try and talk through it. The easy part before 2016, the black line there is historical emissions. This is for China. The blue shaded region there is the former method that we had. So that's mean if you do not allow emissions to go below zero, so zero is the floor in emissions, and you share out, that blue line would be where China's emissions would have to go. So very dramatic reductions. The grey bar, or the grey shading, is where we share out the positive emissions. In the case of China, the lowest part is population, and the highest part is emissions. Many people would think it would be around the other way for China, but China actually has very high per capita emissions. And on the negative emissions, it's the same sort of thing. One extreme is the population sharing, one extreme is the inertia sharing, which is the grandfathering. We add the two together and we get the solid line and the dotted line. So one sort of, it's very hard when there's so many lines in a figure how to label them and put them together. So if you take population sharing for positive emissions, then that means you grandfather, use emissions sharing for the negative emissions, which means that you end up with a black line, which is net. So that would say that China, even allowing for negative emissions, would have to cut through zero in about 2040 or something like that. If you took the sharing around the other way, they could go out to maybe 2060. And this is sort of one of the main reasons of doing this approach, is when would the 0 year be for different countries under different forms of fairness and equity and so on. You can go through all sorts of different countries. I'll just show us a few highlights. This is the US, has very high per capita emissions, which means that a population-based sharing system, it gets a very small quota, which means its emissions need to go down dramatically fast. So the US, in our approach here, would have to be net zero around about 2030 or something like that. If you took grandfathering, which of course the US would favour, that would have to be zero around about 2060 or something like that. EU, I'll skip over. I'll talk about the UK in a couple of slides, and that sort of captures a little bit the EU. India has low per capita emissions, so if you share the positive emissions based on population, which is the grey, if you take the top line on the grey, their emissions go down much more slowly. And this likewise with the negative emissions. So if you use grandfathering for India, India would have to be zero around about 2040, population about 2080. Of course, if you take different methods, those numbers will change. So this figure is a little bit small, so you can squint a little bit, but it compares our results with the image model. So this is the output from the image model in the green lines that you can see on there. And I'll just sort of summarize so you don't have to squint too much. But in a sense, quite surprisingly, in these four regions which we picked out, so the China region, US, Western Europe and India, the positive emissions, the gross positive emissions in the image model follow pretty much our grandfathering sharing based on emissions. And if you look at the negative emissions, as you saw before, the image model has a quite different trajectory for the negative emissions at the global and therefore country level, so you do get some differences. But overall, it's surprisingly similar, given our approach is very stylized and simplified. You will see bottom right there is India. In the image model, India's emissions would be net zero by about 2035 or something. In our method, maybe 2040 or something like that. So There are some differences, but with this sort of modelling approach as a starting point, then you can start to explore the implications of different choices. Originally, we did some of these calculations for a project we had with the UK, led by Corinne Lacuda. And so this is showing the method for the UK. And I don't want to go into the details. There's a few little quirks I want to pull out about this figure. The green lines there and the green dots are the UK carbon budgets. The carbon budgets are in greenhouse gases, so we've done some simplified calculations or estimates to turn them into CO2-only budgets. So all the lines here would suggest that maybe the UK's would have to go down a little bit faster than what it sort of promised, in a sense, for a 1.5 degree. This is all 1.5 degrees. But one interesting thing here is the UK gets to net zero a little bit after the global average, which you would not expect. You know, rich country, blah, blah. You would expect the UK would have to go down faster. And this relates probably to a couple of quirks in the method. You could look at the allocation method, so different ways of distributing emissions. How do you distribute between positives and negatives, not only between countries, but within countries, because you can share your positives and negatives within your own country. Time is up. 15 minutes to go. Yeah. But another quirk on this figure, which is really hard to see, and it took us a while before we stumbled upon this, but the UK's emissions are going down extremely rapidly. I don't know what the number is. It's maybe 5% per year or something. Someone will know a bit better. But when you share out the carbon budget, whatever method we take that we've used here, the emission reductions can go down slower. So there's actually a deceleration in the emission reductions because of the stylized functional forms that we've chosen. Again, maybe you can use different functional forms. Maybe it's related to we've given the UK too much carbon budget. Maybe we should take different forms of fairness and equity and so on into the equation. But this is sort of something that we sort of need to explore. So that sort of summarises the results, and just sort of wrapping things up. Using positive and negative carbon budgets with stylized functions approximates the output of integrated assessment models reasonably well. What does that mean? Is that some sort of verification? Is it some sort of luck? Or we can discuss that. But the outcome is really that this gives you a really quick and flexible method to start to understand processes and implications of different choices and so on. So you can get almost instantaneous feedback if you want to change an assumption. It's possible to share emissions using many different methods. To approximate the way things may happen in reality. So we've chosen very simplified and overly stylized population and grandfathering. There are others. And so next steps, we really need to start to explore out these different options of sharing, different ways of splitting the positive and negative emissions. A bit broader comparison, perhaps, with different integrated assessment models. How do these results compare back? It also tells you a little bit about what equity and fairness means in an integrated assessment model. And hopefully, soon, we'll find the time to write a paper and publish it. Thanks.